and our design. So we have our second heat transfer project, and to do that I have a hot plate which is set at around 400 degrees Fahrenheit, but that's not the important part. We know the energy output is actually 1500 watts, give or take. And we have a piece of carbon steel and a piece of galvanized steel of varying sizes. And we're going to put these two pieces of steel stacked on top of each other on the hot plate, and we're going to measure the temperature under and the temperature over after it's heated up after a while, so that we can calculate the R value and find out how much heat is being put into it and verify those calculations. So the temperature underneath is going to be about 525 degrees Fahrenheit. So I'm going to take the temperature of the top, and that temperature after heating up for a while is about 455. And the temperature of the bottom will be about 485. So let's do the math now. Alright, so let's take a look at the math for this heat transfer. So we have the dimensions for our carbon steel piece and our galvanized steel piece in inches. And I calculated the area, the thickness, which the thickness of each was the same. And I found the conduction coefficients online for both and converted everything to feet so we could find it in BTUs per hour. And the Q was the input required for the hot plate. Okay, so let's start with Q equals T1 minus T2 over R. R being that number that compiles all of the resistances. So it's going to be delta X over K times the area. So we do all that, figure out R, and we plug in our T1 minus T2, and we find that our actual energy required is less than the energy that we put in, which means that the input that the burner required may not have been equal to its output. It might have an efficiency loss. There's definitely extra heat that was lost from conduction and radiation. The temperature gun isn't the best, and so there's a lot of variables that could have caused these not to be equal, but we're in the same ballpark, so we're going to call that real good.